Professor Tomislav Pejković some properties of p-adic continuous fractions.
Thank you very much. Okay, so since I'm going to speak about p-adic continuous fractions, let me briefly recall some basic properties of regular continuous fractions of real numbers. First of all, continuous fraction of a real number is finite if and only if this number is rational. Continuous fraction is periodic if and only, eventually periodic if and only if this number is a quadratic irrationality. And the best rational approximations to a number are its convergence, meaning that if we stop the continuous fraction expansion at some point, we cut off the tail, then we get a rational number which we call a convergent. This is the shorthand, this is the notation that we use instead of writing this large fraction. So this means that if we have another rational number p over q, such that its denominator q is bounded by the denominator of the nth convergent, then it cannot be as good as approximant as the n minus first, and then of course also the nth convergent. Cool. Okay, so this was just a short recap. In the p-adic field, no continuous fraction algorithm has been proposed until now that has all these properties. There are two main types of continuous fractions in the p-adic field, where p is a prime number. Schneider's, which I'm going to talk about today, and Rubin's, which was later modified by Braukin. Okay. So Schneider's continuous fraction is constructed in the following way. We start from a p-adic number which we can take to be p-adic unit. So it has to be congruent to exactly one of the numbers 1 to 2 up to p minus 1, which is a reduced residue set, modulo p. And then we call this number b0. From this difference psi minus b0, we extract the largest power of p, which we call p to the power a1, where a1 is a positive integer. And we take, after we divide by this, we take the inverse, we get the what's called the complete quotient, so the first complete quotient, and we continue this process until we either stop or indefinitely. We stop if some of these complete quotients is actually from this set 1 to p minus 1. Okay, so the continuous fraction can be either finite or infinite. And this is a notation that I use so as not to repeat this large fraction every time. As a short motivation, I chose just one result. So a motivation for using or for usefulness of Schneider's p-adic continuous fractions in constructing numbers with required Diophantine approximation properties. So I'm going to just define briefly the Mahler's and Koxma's function w2 and w2 star at p-adic number psi. So the value of Mahler's function is the supremum of the real numbers w such that this left-hand side inequality holds, where I denote by h of p the height of the polynomial, meaning the maximum of the absolute values of its coefficients. And this is satisfied for infinitely many integer polynomials of degree at most 2. Koxma's function is defined similarly. So we take the value of the Koxma's function w2 star at psi is the supremum of the real numbers w such that this right inequality holds for infinitely many algebraic numbers of degree at most 2. The height of the algebraic number is the height of its minimal polynomial over the integers. Okay, so we know that every p-adic number psi satisfies that its value of Mahler's function is greater than or equal to the value of Koxma's function at this number and less than or equal to the value of Koxma's function plus 1. We also know that for every p-adic number psi which is not rational or quadratic, the value of Koxma's function is at least 2. and the equality between Mahler's and Koxma's function holds for almost all p-adic number psi with respect to Haar measure, which includes also all algebraic numbers. So explicit examples of p-adic numbers for which this difference between Mahler's and Koxma's function, which lies in the unit interval, obviously, and if we want this difference to be some prescribed value, we can do this by using Schneider's continued fractions. So we construct some p-adic numbers which have this difference, a given fixed number from the unit interval, using Schneider's continued fractions. Obviously, we are not interested in when this difference is 0 because it's most of the numbers, including algebraic numbers. So this is the result, which I'm not going to talk about much. This is just a motivation. So we have these b's, these partial denominators are not important, so we can let all of them be 1. What is important is this partial numerators p to the a sub nw, and these exponents. So these partial numerators, we have large blocks of equal partial numerators, and in between these blocks we have some variation. This variation is also introduces this sequence epsilon j, which is here only to show that our construction provides uncountably many p-adic numbers for which this difference between Mahler's and Koxma's function is exactly 1. If we want this difference to be strictly between 0 and 1, we have to give a little bit more complicated construction, but the main idea or it looks similar to the previous one. So we have some large blocks, and then in between these blocks we have some variation in this exponent. Okay, so this is just an example to show that these Schneider's continued fractions are worth a study. So let's go in the other direction. We start from continued fraction, which can be finite or infinite. So Schneider's continued fraction, it has all of these b's are from 1 to p minus 1, and all of these ai's are positive integers. As I said before, if we stop at some point and look at this number, then we get obviously a rational number, which we call a convergent, and this convergence satisfies some recurrence relations, which are written here, and we can put the initial terms inside the matrix and then write this continued fraction, write these recurrence relations in this form, in this matrix form, which is well known. If we iterate this, then we get this product. So if we take a determinant now and divide by qn times qn minus 1, we obtain the difference between two consecutive convergents. We call them convergents, but now it is at this point that we show that this sequence Pn over Qn does indeed converge. So we have that it's Cauchy because we have a precise value of the difference, and so because of the completeness, it has to converge to some number, which can then be shown if we start from this number and do the expansion, we obtain the same continued fraction. So unlike the real case, here we have the exact value because of the non-Archimedean property, or the non-Archimedean p-adic absolute value. This is why we can give an exact value on the difference between on the distance between a number and its convergent. So this is the last line here. Okay. So the first property that I mentioned is if a continued fraction is in the real case, continued fraction expansion is finite if and only if this number is rational. Obviously, if the continued fraction expansion is finite, then this number is a rational number. But since all of these b's are positive, and obviously all of these powers of p are positive, it has to be a positive rational number. So if we start with a negative rational number, we cannot get a finite continued fraction expansion, finite Schneider's continued fraction expansion. And this also happens for some positive rational numbers. For example, this one here. Buncho was the one who showed that the rational number has either a finite or ultimately periodic continued fraction expansion. And if this expansion is infinite, then this period is very simple, just p minus 1 plus p over p minus 1 plus p and so on. So a very short period. There is no complete characterization of rational numbers with infinite Schneider's p-adic continued fraction expansion, although Hirsch and Washington handled some special cases. For example, they looked at when p is equal to 2. So we first modify Buncho's original result to obtain an upper bound on the required number of steps in the expansion before it either terminates or reaches minus 1 as a complete quotient, because when it reaches minus 1 as a complete quotient, we know that from that place onwards we have this periodic part, p minus 1 plus p over p minus 1 and so on. So we know the complete expansion. So the expansion of a rational number psi into a p-adic number, into a p-adic continued fraction, either terminates or the complete quotient minus 1 is reached, and the number of steps required or the number of complete quotients that need to be computed before either of the cases occurs is big O Landau notation, so big O of the square of the logarithm of the height of this rational number. Height of the rational number is just maximum of the absolute values of the numerator and denominator. So from Buncho's proof, we had that this number of steps is big O of the height of psi, so this is an improvement, although in his proof he is not interested in bounding this number of steps before reaching minus 1. However, if we are only interested in whether the continued fraction expansion terminates or not, we don't have to go all the way up until we reach minus 1 as a complete quotient. As soon as we have some negative number as a complete quotient, we know that the expansion cannot terminate. So we also have a result for this. If so, we take lambda to be some constant depending on the prime number p. And if the p-adic continued fraction expansion of a rational number psi is infinite, then within this many complete quotients, we have to have one which is at least one which is negative. And this bound is in general asymptotically best possible, as shown in the next example. So we set mu n to be a rational number with this p-adic continued fraction expansion. This means that this block p1 repeats n minus 1 times, so this is 1 plus p over 1 plus p over 1 and so on until we reach p squared over minus 1. The complete quotients of this number starting from the last one and moving backwards are minus 1, which is negative, then the next one is 1 plus p squared over minus 1, which is also negative, but the one before that, which is 1 plus p over 1 plus p squared over minus 1, it is positive. So all the rest before that obviously also have to be positive. So this implies that in the continued fraction expansion of this number, the first negative complete quotient is obtained in the n minus 1 step. And we can also calculate the height of this number, insert it into this expression in the theorem, and show that this is really asymptotically equal to the number of steps required before reaching the negative complete quotient, first negative complete quotient. Okay, moving on to approximation by rational numbers. For rational approximation in real numbers, it is enough to bound the denominator of the rational number, because if we bound the denominator, then we also bound the numerator. If a number is close to some other number, then we can do this. For approximation of a p-adic number, we have to bound both the numerator and the denominator of the rational approximation a over b, since this difference, p-adic absolute value of big psi minus a, can be as small as we like if we only bound the size of the denominator. We can set the denominator to be as small as possible, equal to 1, and we take a to be a number which is congruent, integer which is congruent to psi modulo p to the power k, where k is some large number, as large as we want, and then this difference is obviously can be as small as we want. But even with this restriction, even with bounding the numerator and denominator, the convergence in Schneider's continued fraction do not have this nice property that the convergence of the real numbers have. So they are not necessarily the best rational approximations. So there is a link between the quality of approximation and finiteness of the expansion. Let psi be a p-adic unit and a over b a rational number written as a reduced fraction. We slightly change the terminology and say that the rational number with the reduced fraction u over v is a better rational approximation of psi than a over b if this first inequality holds, while the numerator and denominator are bounded respectively by the numerator and denominator of a over b, with at least one of these bounds being strict. So the result is a rational number with the reduced fraction u over v has an infinite p-adic Schneider continued fraction expansion if and only if it is a better rational approximation of some psi, some p-adic number psi, p-adic integer psi, than some convergent of psi. Okay, so this links the quality of approximation with the finiteness of the expansion in the Schneider's continued p-adic continued fraction. Okay, so we proved that a better rational approximation in our terminology than this k minus first convergent does not exist if this inequality 2 holds, which means that the sequence of these exponents in the partial numerators, so in this p to the power an, which we had above, this sequence has to grow quite rapidly in order for this to hold. And one sufficient condition for the existence of such approximations, so for existence of better rational approximations than this convergent pk minus 1 over qk minus 1, is the one in 3, inequality 3. This shows that it is of interest to find good estimates of size for numerators and denominators of convergence given sequences with different rates of growth. And I think, although I have a lot more slides, I think this is a good time to stop my talk. Okay.
Thank you very much for the very nice presentation. Are there any questions or comments?
Yes,
Can we find the fundamental unit of a real quadratic field with that method?
I don't know. I didn't look at this at all. Yeah, but most of the results are on the periodicity of expansion of quadratic irrationals, because it doesn't have to be periodic.
Further questions or comments? If not, then let us thank the speaker again.